statistics students. Hopefully so far this 5-week class is coming along very well for you all. This video right here, I've called it Chapter 5 Tutorial. And it seems that a few of you are kind of having some trouble here with Chapter 5. So what I'm going to do, I'm going to actually present this in a couple phases. First, I want to remind you all of how to study for this class. And then I want to kind of briefly talk through some of the main things that you should feel good about already before you even start Chapter 5. This class has a fast pace. It's very important that you learn the fundamentals, which does take more time to correctly learn fundamentals. It's very important that you learn the fundamentals so that as the class gets harder by about week 3, so that you are successful and not simply struggling, because it will become harder to just get by. So first, let's kind of remember ways to study and how to be successful in this class. The first thing you should always be doing would be thoroughly reading and working through all examples found in As You Learn. These notes that I have provided for you, these notes that I have provided for you are actually exactly the same notes that a regular paced semester class would go through, including the exact same examples that I teach. You simply have the answers because I'm letting you work at your own pace instead of forcing you to watch hours and hours and hours of teaching. So, because I understand some of you all may be able to read, process, get the idea, highlight, whatever, and you want to keep moving forward quickly. In addition to these notes, you have PowerPoints that all students are always expected to read. These are from your textbook. And then, of course, you have a textbook also in Pearson. Both of these things are in Pearson that you want to read through. Now, if you do like videos, even though me actually working through all of these examples for you would require probably 5 hours minimum for you guys of videos per day to stay caught up with, some of you may still like to hear someone talking, to see someone writing, that sort of thing. The first go-to place for you should be within Pearson. And in the intro video, I showed you how to find the mini videos, they're short videos that they already have for you. Also, when you're working the problems, sometimes you can ask for small videos if you look at the Help Me Now option. So these are the places that you go to first. You all will still discover that this course is challenging. And that's why I think it's incredible that the fourth place some people are going to is Facebook. This is where you all give comments to each other to give each other support, and even videos sometimes, earning up to 5 points per test. You get 1 point per comment. You get 3 points per video. So after trying Facebook, I monitor Facebook very closely too. That's when I step in and give you extra videos. So that's where we are right now. I'm stepping in because I know that we have several students who are working very hard, who have already communicated some issues with Chapter 5. Again, that's phase 1. I know it's not very exciting to hear me repeat this stuff. It's just very important that you guys know very clearly how to be successful. Do not skip these steps. So before we even get into Chapter 5, what should you already know? What should you feel very good about? And if you don't feel good about it, what should you reach out to me about or go back and read a little bit better? Well, first of all, you should be very clear from Chapter 1 regarding statistics. What is statistics? You should know that statistics is the study of variation. And we study variation, we study these patterns in an attempt to discover, to identify the truth. Sometimes we simply want to describe the truth that's been happening. Other times we may want to make predictions about the truth. Right? I have a sample, maybe. And I look at the pattern of the sample and then I say, okay, well now what do I expect to happen if I have a similar scenario again? I'm sure even without reading all the material, you can understand how lucrative this would be. to be able to say, hey, I know exactly how many people will buy this fashion type if we start to promote this style, right? Or what size jeans we should have on the market, or what time I should put my commercial out there, or which coupons I should send to certain people, or what medical things are going to be the most beneficial for my consumers. What should be on social media? What do I do if I want to get elected for office? How can I monitor human behavior and look at what I already know, right? It's incredibly huge. It's an exploding field, actually, that this generation is seeing like no other generation before, because we have so much access to data from cell phones, from Google, from Facebook, everywhere. It's been around for a long time, but now it's just a whole new level. The variety of data that we have, even from within hospitals. We can now help prevent sickness because we can look at diagnostic information. Well, we can look at information to help us, I'm probably using the wrong words, to help us make diagnostic decisions before the actual sickness has kicked in. It's incredible what statistics can do for us. But we know that every person is different, right? We know that there's this variation, this change that happens from one human to another, whether it's their network of friends, whether it's how often they do a certain behavior, maybe which grocery store they go to, maybe what their symptoms are before they actually get sick or have an infection. What food choice they're going to pick if they've chosen this other stuff in the past. Like these decision things that it comes from us understanding the differences from person to person and understanding that difference in order that we can identify the truth. What does everyone really think? Who is really going to get elected? Should I really put my store here? Am I actually going to have consumers, or will I go out of business, right? Sentiment type things. Will this product survive on the market? So
I hope that you all are excited enough that you do what it takes to learn this material well and to begin to engage statistics in a way that could potentially change your career path. So beyond what is statistics, let's see. I'm having to dub over the sound because it messed up before. Beyond what is statistics, we learned about some data types, or you all should have learned about some data types. There's actually a lot more subgroups besides just categorical and quantitative as far as classifying data types, but this was a good start for you all at the introduction to statistics level. And the reason that we like to differentiate between categorical and quantitative is because it does change which graph types we are able to use. So categorical, we said the most basic definition would be generally non-numerical things. Not always. Of course, some numbers, such as a Social Security card, or excuse me, Social Security number, could be considered categorical. Some of the graphs for categorical included pie charts, it included bar graphs, or Pareto, if you put those bars in order from highest to lowest. Two-way / contingency tables, those were a big one. Generally, nothing that you would that would make a difference if you mixed up the order of the categories or the labels. Quantitative is a bit different. Generally, you're looking at numerical data, specifically numerical data that math operations can be calculated on. Again, there is a hierarchy, so even within quantitative, we have a hierarchy of being able to do more things with information that's more numerical. Let's say it that way. So for example, maybe I can do a lot with someone's weight if I'm collecting weights from different people, especially because those tend to be continuous numbers where we can get lots of different decimal type numbers in between each option. So yeah, quantitative numbers, math can be done on these numbers, and the graphs for quantitative would include, well, that's not really a graph, but it would be a table called a frequency distribution that we tend to make. Hopefully you saw that in the reading, where we tally up or make notes of, hey, this group right here between this range, we have this many of this category occurring. We also have a histogram, which is one of the most popular graphs. We have dot plots. We have box and whisker graphs also. So as we're talking about quantitative data specifically, the shape comes into the discussion. You know, how many buffs do we have on the picture? Is it unimodal? Is it bimodal? Does it have more than two modes? You know, is it multimodal? We talk about symmetry. Is it a symmetric picture? Because that might change our ability to make decisions as we look at the graphs and try to make predictions about the truth. And for clarity, when I was talking about truth earlier, I said exact. I probably was a little bit not careful about that. Really, when I'm saying exact, I'm saying within an interval. Like we're predicting, and even then it may not be perfect. Also, of course, we know that with that variation that we're caring about in statistics, outliers do occur. So that's something else. Does this picture have outliers? Are they extreme? So here you see me drawing a picture of a sample histogram. The bars on this thing would represent the frequency. The height of the bars would represent the frequency. Sometimes statisticians will also let the height of the bar be relative frequency, which is where you take the count, the frequency, and divide it by the total number. Basically, it just makes every bar's height the percent that it would be of the total. The nice thing is the pictures would look the exact same, except the scale and the y-axis would be different between frequency and relative frequency. So we have histograms that are a pretty big deal. Check your notes on as you learn, because there are some commands in StatPrints that can help you create histograms and even figure out if your data is approximately normal or what it is you're looking at. Histograms typically are separated into classes, and order does matter on these things from left to right. So each bar technically would have the same width, by the way. This is just a rough sketch. And there's some characteristics on a histogram that we tend to gravitate towards. First of all, the measure of center. Mean is our favorite on a histogram. It is true that on a perfectly symmetric histogram, the mean, the median, and the mode will all line up together. But outliers can really affect the mean, you see. And of course, the mode would be, the place where the bump is occurring. So sometimes you may even have more than one mode if you're not looking at a unimodal picture. The mean is what we tend to use on a histogram versus a box plot, where we can still try to understand the data. But we create these, we first put the numbers in order, usually from lowest to highest, or whatever, they have to be in order. And then we kind of chop up the data, representing the center of the data, the median, as Q2. Below this box plot, you'll see that I drew a line with some little interval bars. What I'm trying to show you here is that it's literally like having a number line under the box plot. And so the Q2 would take place exactly at the center place within those data values. And then of course you have the minimum being the lowest, the max being the highest. Sometimes you'll see graphs that go all the way out and show even the outliers, but usually the more advanced box plots would use a star for that, so that you can tell that something's super far away. Q1 and Q3 are the upper and lower quartiles. So again, we have mean that usually statisticians like to put on histograms, maybe adding some other measures of center also. And for box plots, median is that Q2, that's showing the center. Check out the cat nose on that box plot. Hopefully as you've been studying, you've been learning that really when you're looking at a box plot, you are looking at the balance of the data. Because we know that every single section, between the min to Q1, between the Q1 to Q2, on and on, every single section has exactly 25% of the numbers in it. In other words, if we had 4 numbers, there would be, for each 25%, we'd have 4 numbers that took place between the min and Q1, 4 numbers between Q1, Q2, 4 numbers between Q2, Q3. You get the point. And so what we're doing is we're marking off those thresholds, and so whenever we see more distance between, for example, Q2 and Q3, that tells me that those 4 numbers that fell in between them were further apart. So we're looking at the spread, noticing on the box plot that on this one I drew, it seems to be kind of clustered together on the left. We'll come back to spread on box plot in a second. Looking over here to the left, just so that I've written variation and standard deviation notation. The X bar or Y bar, the S squared, and the S are all notations that are used for sample data. I'll come back to that later in this video. But for right now, the idea is that variation is kind of one step earlier than standard deviation in the creation of this formula that describes the average distance that any point is expected to fall from center, or just the average distance that points are from the center. Like literally the average is taken of those distances. We just had to square them to make the negatives go away when we're subtracting, and then square root it. So that's how we talk about the spread of the data on a histogram. We start to talk about that average distance from that X bar that you see I've marked there. Now on a box plot, notice I just now drew a sketch over the box plot. Some people don't like this too much, but I actually kind of like to imagine that that smooth line, like I had over the histogram, over a box plot too, because you'll notice the bump on the data is more to the left. This is definitely a skewed right picture, where the tail extends on the right-hand side. So with a box plot, We want to notice things like, for example, like I mentioned a second ago, how Q1 and Q2 are closer together than Q2, Q3, which is my way of being able to tell that the data is clustering closer on that one side. So it's another way of talking about spread. Another characteristic that would talk about spread would be something as simple as range, the max, subtract the min, but it's not really as useful. So with a box plot, if we want to talk about the spread, we tend to go towards something called IQR, inner quartile range, which is where you take the upper median, that Q3, and you subtract the lower median, Q1. And the benefit of this is, if you guys caught a second ago, I said that every single little section here represented 25%. Well, the benefit would be between Q1 and Q3, that's the center 50% of my data. You'll notice soon with histograms that we like to talk about center data a lot, and we'll talk about the empirical rule to talk about starting at the center plus or minus how much on each side is what percent. So center 50% is a pretty good starting place for our box plots. Now speaking of describing our data, we also have outliers. So you'll see up here I'm writing outliers. If you take the mean plus or minus 2 standard deviations or the mean plus or minus 3 standard deviations, using the histogram mentality, and later on it will just be a curve, a smooth curve we tend to look at later in stats. But the empirical rule starts to come into play. And using that empirical rule where you're going to learn that 95% falls within plus or minus 2 standard deviations, we would say anything beyond that would be unusual. And 99.7% of our data is typically found within plus or minus 3 standard deviations. So we would say that beyond that, we are very unusual. So another way of getting outliers would be to look at this box plot and to say, okay, well, Q3 plus 1.5 times that IQR width, or Q1 subtract 1.5 times that IQR width, literally like you're using a ruler on this number line. And this tells us whenever we have an outlier via using Q3, Q1 with the IQR. Another way would be to use 3 times the IQR for the very unusual sort of outliers. Now what I would like you to notice over here at the histogram is that the mean and the standard deviation are often referred to this way when it's a sample. In a moment I'll show you the notation that you're seeing right now in the text for mu and sigma, those Greek symbols. But it will be the same idea, and it will be looking at a z-score. So a lot of times when we're talking about z-score, we are talking about normalizing something that is bell-shaped down to a standardized shape. So looking at this as you go through your class notes, I know they're hard to see here, but as you go through your class notes, you want to be noticing things like, hey, well, what happens if I take a certain data value and I subtract or add something to it? Okay, well, it shifts the data back and forth. What happens if I take a certain data point and I multiply something to it, or divide something, So kind of the beginning of chapter 5 starts to look and say, well, is the z-score okay? Or is it tearing things up? And hopefully what you saw with the z-score was the idea that the percentages that you see under that bell curve, under the standardized or normalized version of the bell curve, called the z-distribution, that is the equivalent of the percentages that you will see on those original type of pictures that had the bell-shaped behavior that we've talked about already. Now, again, X bar and S for standard deviation, these symbols are technically for sample. So what I'm trying to do here with this picture of the histogram is to help you kind of go from the sample data that you were describing early on into this discussion of chapter 5 when we are assuming that we have population data, and then later on we will discuss examples where it clarifies what we actually have and we try to decide if it's a sample or a population. So instead of seeing X bar as we talk about z-score, we're going to be talking about population, the everything. So maybe everyone that we are concerned about in this group, we have information from them, so we know everything already. Mu, you see in quotes there, I have MU, that is the population notation for the average or the mean. And then again, X bar or Y bar would be the same thing. It still means average, but it means average for the sample. You'll see a sigma, which looks like a sideways 9 squared, and just a regular sigma that looks like a sideways 9. Both of those match up like you see on the screen here. Sigma squared is variation for the population, and a plain sigma would just be the population standard deviation. So back here now to the z-score. You can see that it's an adjustment where you take some x, some original value, you subtract the average from it to get that deviation, that distance, and to get that distance that that particular value is from the average, and then you divide it by that average step size from the middle to normalize it down. So x is the value that we tend to be putting in there. You may see y also in your notes, but that's the one that we are normalizing. Look at the picture now in your class notes. Again, in As You Learn, you probably have a clearer view, but look at the picture now for the empirical rule. As you look at the empirical rule, you will already see that these class notes actually have some percentages already laid out for you, some little wedges. But my recommendation is that you learn the empirical rule based on standard deviations also. Before I go back and go through that bell curve with you, let's talk about that z distribution that I was bringing up a second ago, the one that we said you could normalize to get, right? So the z distribution is a normal bell curve. Oops, hold on. Is a normal bell curve. And on this bell curve, we have a mu equal to 0. The center is always exactly 0. And we have a standard deviation equal to 1. I'm not sure why this is not moving. So something like this. Okay, so mu equals 0, standard deviation equals 1. And like I said a minute ago, the percentages under that bell curve are the same, actually, as they are on top. So let's go back to the top now and talk about the empirical rule and what it says. Plus or minus 1 standard deviation, you see that I just now marked that on the picture with a 68%. Plus or minus 2 standard deviations, I'm marking that with a 95%. So we're saying that approximately 95% of our data will fall within plus or 2 standard deviations of the mean. And then you see a 99.7% for plus or minus 3 standard deviations. Now, like you saw a second ago when we were talking about outliers, we use these ideas, this 95%, and say, hey, if something's outside of that center 95% on the left or right, it's unusual. If something's outside of the 99.7% on the left or the right, it's unusual. So again, remembering this idea of an outlier and what it meant to be unusual or very unusual. That came from the empirical rule. Also, please notice that we never say we have 100% certainty or 100% of our data ever. We know that 100% is being represented by the picture under the bell curve, but please notice the bell curve never actually touches the x-axis or z-axis if it's the z distribution. The tails are always kind of floating in the air to suggest that there's always some chance that something could have happened on the left or on the right-hand side. So the z-score that we're using and that I'm going to demonstrate for you in the examples, the z-score is used as our bridge to go from original data to normalized data. What you see me pointing at here, again, I know it's hard to see, but I'm reminding you that within the notes right here, you have instructions on how to use StatCrunch, and these instructions tell you how to make a normal histogram type picture to know if something is normally distributed, and they also remind you how to get that normal calculator. So here's the first example from your class notes. You were given some information. You have SAT scores, and you're told that the average SAT score is 500 and the standard deviation is 100, and you are asked to please figure out the percent of students that you expect to be below 600. So the notation that you want to notice here is that we're using n and in parentheses 500 comma 100. That notation always will say what is mu, what is standard deviation sigma in that same order every time. And the n stands for it's normal. We're saying it's a normal distribution. So it has those attributes that we've learned about, the unimodal, the symmetric, things like that from before. And it's also continuous. Okay, so let's draw a sketch here. And I do recommend that you guys get into the habit of drawing sketches as you work problems. So on this sketch, you're going to notice that I'll label mu equals 500 and standard deviation equal to 100. then I go on here and I write 600, which is my x value. Area to the left for less than, and we are looking to see what that percentage is. So now let's go over to Pearson and pull up StatCrunch. StatCrunch is on the left, and I clicked on View StatCrunch website and then Open StatCrunch. Now I will click on Stat, Calculators, and I will go to the normal calculator. Okay, over here we have mean. We're putting that mean of 500. Standard deviation, we can input 100. Oh, actually, we should turn our sign. It should be shading to the left, so let's use a less than symbol. And the x value always goes inside parentheses, or z, if it, whatever's on the number line. And then on the outside of these parentheses, you'll notice that's the percent. So I'll put less than or equal to 600. When we compute, we get 0.84, and there's some decimals I can't quite see there, but I'll write for you in just a second. So that's using StatCrunch. Now the thing is, we did just now talk about the empirical rule, and you do want to be able to have this memorized rule. I mean, you guys do get a cheat sheet, but in real life, hopefully you're going to get so good at this that you will kind of memorize it, that gives you a fast solution so that in a regular conversation you would know if something sounds somewhat okay or not. So let's use that empirical rule that we've just discussed, remembering that the empirical rule does have the prerequisite that your data must be approximately normal before you can even use this rule. Right. And then, so when we go back to the picture, we're going to start with that average, that mu in the center, and we're going to use this mentality of the plus or minus 1 or 2 standard deviations. Actually, if we look at this, we can see that 600 is exactly 1 step size, 1 standard deviation above 5. So let's use plus or minus 1 standard deviation. So I'm writing 68% right here, between plus minus 1 standard deviation. So remembering a second ago I said that the area under this bell curve is equal to 100%. What you should think about now is, hey, I know this little wedge is 68, so if I want to know the area of the two edge pieces now, the shaded one and the not shaded one, well, I can say 100 subtract 68 to get the area. So let's see, 100 subtract 68, that will be 32%. Okay, and that is the area in both edges and both tails. So what we'll do to get just the area on the left is we will say, okay, we'll divide that by 2 because this is a symmetric distribution. So that gives me 16%, meaning that based on the empirical rule, that 16% on the left plus that 68% in the center will give me the approximate percent that we are expecting for a number of students below a 600 on their SAT. We're getting approximately 84%. And again, remembering that StatCrunch gave us a more detailed or more specific answer. Usually it's a little more accurate because it's not saying approximate, even though we know that all statistics is not going to be actually exact as we do things. But right here we have an 84 and 0.13% chance or percent of students with the StatCrunch. I do not recommend that you ever use tables. Tables will slow you down and possibly make you not able to finish the exam. So please learn the empirical rule. Please learn StatCrunch well using that normal calculator. It will be the difference in you doing well on the exams versus you not doing as well. So let's look at the next problem that was on that homework sheet, the idea that we were looking for above 700, and you'll see there we have 0.0227 coming up for the area above 700. And again, you could kind of draw it out because that 100 is an exact step size. And we're seeing 600, 700. You can do empirical for every single one of these. Now for the between question, that shouldn't be much harder for you. For between, if you're using StatCrunch, all you need to do is go over here to the picture and click on between. So you'll see here, let's see, the between is up above the picture. You can see in my original video, I think I was talking about the same stuff, maybe slower, who knows. But you'll see between on that calculator, it's in view right now. Okay, so for the last problem, you are asked, what is the 95th percentile of SAT math distribution? So for percentile, that's referring to cumulative area to the left. And 95th percentile, obviously that's in percents. So we're saying, what is the cumulative area to the left of 95%? So it's kind of a different structure on our picture. Let me jump ahead to where I draw this for you. So here we still have 500 in the center. We still have a standard deviation of 100, and we have 95% under that bell curve on the left-hand side. Again, cumulative whenever it's a percentile. Even a quartile would be cumulative. A quartile would just be in chunks of 25%. So if I said the first quartile, I'd be saying 25, second quartile 50, third quartile 70. You know, the same kind of reasoning holds. Just percentiles are actually the easiest. So to look for that percentile, I'm going to actually still have mean of 500, standard deviation of 100. 0.95 should go on the outside, and you'll see that 664 point something is what's coming out of the inside of those parentheses on this calculator for my x value that lines up to that percentage. So you kind of work backwards to get that appropriate x value. Now let's look at one more problem. You'll see several here that give you some good kind of brain teasers on please find this percent, or please you don't know your standard deviation, or you don't know your mean, things like that. You don't know your mean or your standard deviation. So there's kind of some brain teasers. I'm going to work example 5.4 with you because it's similar to a question that your group specifically had that was posted earlier. So this problem says scores on the final last semester had a mean of 70. If 75% of students scored below an 82, what was the standard deviation? So again, we're looking at bell-shaped distributions, and we label mu as 70. We have a standard deviation that we don't know. And we are given a percent. We also know the x value. X is equal to 82. Now notice the 82 is bigger, higher up than the 70, so I'll put that to the right, of course. And then my 75%, I chose to write that as a decimal this time and shaded it below that 82. So this is the picture of what we're looking at. What is the standard deviation for this scenario? Now you may remember that one of the biggest ideas in Chapter 5 was this idea that we can compare different things, different groups completely, in a normalized way so that we can talk about them better. Read your textbook if you haven't, and it talks about the Olympics. There's some really good applied examples. But we know that the z-score is a good way to get things down to that normalized or standardized language for us. That's the bridge between original to z distribution that has the mu equals 0 and standard deviation equal to 1. So we have original versus normalized or standardized. So what we can do actually, because those percentages should maintain, they will maintain the same amount between the two bell curves, is we can actually use the z-score to solve for standard deviation. But I guess first we need to figure out what is z. So let's sketch a new bell curve. And actually, I'm going to remind you guys of what the z-score is equal to, x subtracting mu over standard deviation. Again, reiterating that it is the bridge to go either direction, from original to normalized, or normalized back to original. So it's like the secret piece in your puzzle. It's also, again, good for taking people from different groups or items from different groups and putting them on standardized scales so you can think about them in similar terms relative to their peers or relative to whatever you're comparing them to in the main data. Okay, so here we have our z distribution. Notice I put 75% to the left of a z. Again, notice I used z, not x, because on this lower picture, this is a z distribution. So on the x-axis or on the main axis, it's now a z that we're looking for. Let's go over here to our normal calculator. We know that the z distribution always has a mean of 0 and a standard deviation of 1, so we'll put that in. We do not know what z is, so we'll clear out that number line value, but we do know the area that has to go with it. P does stand for probability, or you can think of it as percent. So that's one way to help you always remember that when you have a percentage, it goes on the outside of the parentheses over here on the right. So 0.75. and we get a z-value of 0.67. Remember that z-values are usually a lot smaller than the original values that we're seeing. That's because we're saying how many steps on average are we from the exact center. So this particular value was less than 1 standard deviation above what was typical. So let's go back now to our problem. There we go, okay. And we have z equals 67/100ths. So now you can see from our z-score that we have z, x, and mu, all pieces of our puzzle. Now we simply use algebra to solve for sigma. So here I'm writing 0.67 in place of z. I'm writing 82 in place of x, my value that we're using. My average is 70. I'm using the original values on the right-hand side of that equal sign. And we're solving for sigma. So using algebraic steps, you could actually put the numerator together first, but I didn't. I multiplied both sides by sigma to cancel that out off the denominator. And then I say, okay, well, 0.67 times sigma is equal to, that took a second here to use my video because I double-checked my math in the calculator. We get a 12, and then we divide that 0.67 off of sigma to solve for the standard deviation that goes with this problem. So standard deviation comes out to be about 17.9. I do round here. If you want to check your answers, since they were kind of brain teasers, you can. Remember that when we're rounding in places, things won't match up exactly, but they should match pretty closely. So let's go over here and just check for fun. Okay, well, we're putting in that mean of 70. We're putting in that standard deviation that we did round, that 17.9. It will change things a bit. That's okay. It gives us a general idea of if we're kind of in the ballpark. And we were looking for less than 82, and look at that, we got almost 75%. Again, not exact, it's 0.74 or something, but it's pretty close considering that we rounded the standard deviation right there. Okay, you have a few other problems here to try, and I encourage you to definitely try 5.5, which is a similar strategy, and 5.6, which is both mean and standard deviation unknown. Remembering that once you get your answer, you can do what I just did to kind of check yourself and see if your answers are in the right ballpark. Now, both the mean and standard deviation unknown, example 5.6 is the most challenging. A lot of your class notes you will notice, a lot of times they have the answers, but not always. So as you're working these, please reach out to me if you're not sure if you got the right answer. I'm happy to check your work, and it shows me that you are being a great student when you send me pictures of your notes and say, hey, is this right here what you were looking for? The trick to 5.6, by the way, is to use standard deviation 2 separate times. So you should have either one bell curve labeled with two different, like an X and a Y or something, or you can make 2 bell curves and then normalize each of those and solve. It's kind of tricky because you have to know how to solve when you have 2 variables and 2 equations using probably substitution. Some people may like elimination. Something like that's what you would use. So it's more fancy with the algebra, not so much with the stats. Also, in the first example, 5.3, when you saw that Z with a little subscript of 0.05 and a Z with a subscript of 0.95, that does just mean percentile. So keep that in mind, okay? So when you see Z with a 0.05 hanging off of it, that's saying 5% to the left of that Z. Okay? Happy working, you all. This video has been a challenge. Hopefully this new record over will help you, though. That is my hope.